If I were a manager and I said to you, all right, write me a function that draws a shape on the screen, you would ask, well, what kind of shape are you talking about? You can't write a program to draw a shape if you don't know what kind of shape it is. So shape is an example of an abstract class. Likewise, option is an abstract class. What kind of option? Is it a European call option? Is it a European put option? Is it an American call option? So option is an abstract class or category that we have a general understanding about, but we can only describe and compute prices for specific kinds of options. Here on slide 9 is one way of implementing a shape class. We're saying that a shape has these three virtual functions: draw, rotate, scale. And we could come up with other operations that we ought to be able to do on shapes. But there's nothing really useful we can do to implement these functions. On slide 9, we've provided these silly implementations where the definition of each function basically says, sorry, you can't do this. So if you have a shape and you say you want to draw a shape, you'll get a message on the screen saying, no draw shape, and so on. Now, if we can't actually draw or rotate or scale shapes, then what good is it to have a class shape in the first place? Well, the benefit of this is that we might want to have collections of shapes. That is, we might want to have lists of shapes, or trees of shapes, or vectors of shapes, or whatever. In the case of options, we know that we can have a portfolio of options. We can't price an option without knowing what specific kind of option it is, but we can use this base class option to set up a portfolio, which perhaps is a list, of pointers to options, where actually each pointer to option is pointing to a specific kind of option, that is, a European call option with appropriate parameters, or an American put option with appropriate parameters. And then we can traverse through our portfolio, our list of options, to compute prices for each one of those. To create a class that is truly abstract, what we do is to define our class to have at least one so-called pure virtual function. A pure virtual function is a function that has no implementation. And the notation that was developed to specify that a function is pure virtual simply involves using the equal sign and 0 instead of a body of code for the function. So in this example on slide 11, shape is truly an abstract class. A shape has a draw public member function, it has a rotate public member function, it has a scale function, but the shape class itself does not define any code for those functions. The functions are virtual, and therefore specific implementations of these functions, specific overrides of these functions, must be defined in each derived class. So if we say that a square is a kind of shape, then we have to implement draw and rotate and scale for squares. And if we say that a line is a kind of shape, we have to implement draw and rotate and scale for lines, and so on. If you specify at least one pure virtual function in a class, then it becomes impossible to declare objects of that class. In main, if I attempted to say shape space s and ran that through the compiler would print an error message saying shape is abstract. You can't have this object called s. So here on slide 12 we have an example of an actual or concrete class derived from this abstract shape base class. This is class circle. A circle is a kind of shape. Is a kind of is indicated by :public shape. And this class has a constructor which will create a circle by setting its horizontal and vertical offset for the center and also the radius. It has a destructor which in this case there's no dynamic memory we have to deallocate or anything. So we're simply displaying a message to indicate when the destructor is called. Then we have to write the code for drawing a circle, which is a little more complicated than I'm going to try to do here. We have to write the code for rotating a circle. Now, rotating a circle is completely trivial. We can implement this function by creating an empty body, because a rotated circle is indistinguishable from the original circle. Down in the private section, we need to have the data necessary to keep track of the state of the circle. Each circle object is going to have an XY center position as well as a radius. We're not going to allow default circles, and so we've declared the default circle constructor to be private. Similarly, here we have a concrete class, Polygon. A polygon is a kind of shape. Polygon has a constructor and a destructor, draw, rotate, so on and so forth. Now, the data members that we need to keep track of a polygon are quite different from the data members that we had for a circle. In the case of a polygon, we're going to need x and y coordinates of all of the points, and here we've chosen to do that by using dynamically allocated arrays of ints for the x coordinates and for the y coordinates. We also have to keep track of the number of elements, the dimension of these xy coordinate arrays. And as a circle, we're not going to allow default polygons. If you want a polygon, you have to specify the x coordinates, the y coordinates, and the dimensions of those two arrays. Okay, those are the three parameters that you're required to give to the polygon constructor. The implementations of these polygon functions are shown here on slide 14. We're not showing draw and rotate, but here are the constructor and the destructor. In the constructor, we're first examining the value of the dimension d to make sure that that's a positive number. We can't have a polygon of 0 or fewer points. So, for the array of x coordinates, if d is greater than 0, we're going to allocate a new int array of size d. Otherwise, we'll set xa to 0, that is the null pointer. Likewise, for the y coordinates, if d is greater than 0, we'll set ya to point to a new int array of dimension d, otherwise null pointer. And finally, we'll set dim, the dimension, to either d if d is greater than 0, or 0 if d is less than or equal to 0. Now, once we've established these dynamically allocated arrays of ints for the x coordinates and the y coordinates, and we've also established the dimension, in the body of code, we'll use a for loop to step our loop counter I from 0 up to 1 less than dim, and we'll copy the values from the input arrays, px and py, into the current polygon object's internal arrays, xa and ya. Now, because we use dynamic allocation in the constructor, we'd better remember to delete those dynamically allocated arrays in the destructor. In fact, this is why we use dynamic allocation in the first place. It would frankly have been simpler for us to use a couple of vectors of ints, since we know about the vector class now. But I wanted to remind everyone that you have to undo in the destructor any resources that you allocated in the constructor. In this case, we have to delete these dynamically allocated int arrays. As we did in the circle class, we're also displaying a message here that will appear on the screen each time this polygon destructor is called.